Hello everyone, Nick here and welcome to my channel. In today's video, I'm going to walk you through a super simple way to train a YoloV8 model for custom object detection. I'll be creating a model specifically to spot the European perch, this beautiful little fish I have got on camera during my underwater adventures. I'm doing this just to show you that we can train a model to detect pretty much anything, whether it's a rare fish, a unique object, or something totally random. I'll guide you step by step through the entire process. We will start with how to gather the right data, an essential first step for any object detector. Then dive into annotating the data using a popular computer vision tool and structuring it just right for YoloV8. After that, we will train the model locally, and finally, we will test its performance to see how well it has learned to recognize the European perch. By the end, you will know everything you need to train a custom YoloV8 model, so you can create your own detector for whatever unique objects you want. Let's dive in and make this happen. First of all, let's talk a bit about what YOLO is and why we are using it for this project. YOLO stands for You Only Look Once, which refers to its ability to analyze an image in a single pass, making it one of the fastest and most efficient object detection models out there. YOLO is known for real-time object detection, meaning it can recognize and locate objects almost instantly in video or image streams, which is why it is so popular in computer vision projects. In this video, we are using YoloV8 to recognize a unique object, our fish, the European perch. But this process can work with any custom object you want to detect. With YoloV8's flexibility, you will have a powerful tool for creating highly specific object detectors that run efficiently on just about any setup. So, with that understanding, let's get started on building our very own custom object detector. Let's quickly go over the 6 steps to train our model. Step number 1. Set up Python and YoloV8 to get our environment ready. Step number 2. Create a dataset by collecting images of our target object, the European perch, from various angles and settings. Step number 3. Annotate the dataset, drawing bounding boxes around each instance of the object so YoloV8 knows what to look for. Step 4. Split the dataset into train and validation folders to separate the training images from the validation images. Step number 5. Train the model using the labeled data, letting YoloV8 learn the patterns needed to recognize our object. And finally, step number 6, we have to test the model to see how well it performs and make any adjustments if needed. With these 6 steps, we will have a custom trained YoloV8 model ready to go. Let's start at once. First, we need to install Python and set up our environment. At the time of this recording, YoloV8 is not compatible with Python 3.13, so we will be using Python 3.12.7 instead to ensure everything works smoothly. To get started, go to the Python website, navigate to the download section, and find version 3.12.7. Download the Windows installer. Once the download is complete, open the installer. Before you hit Install Now, make sure to check the box that says Add Python to Path. This step is essential for setting up the environment correctly. After that, click Install Now and Python will be installed on your system. Next, we install the YoloV8 library. YoloV8 is part of the Ultralytics package. To install it, open a terminal window and type the following command: pip install Ultralytics. This will install YoloV8 along with any other required dependencies. This will take a few seconds. Okay, the installation is now complete. To test that YoloV8 is set up correctly, let's create a simple Python file that imports the YOLO library. First, let's create our project folder. I'll create it on the desktop and I will name it Fish Detector. Inside this folder, we create a new Python file called train.py. We will use this file to train our custom model. I open the file with Sublime Text and add the following code. Import ultralytics. Print parenthesis f quotes using ultralytics v curly brackets ultralytics dot underscore underscore version underscore underscore. Now if I run this code, we see the message using ultralytics version 8.3.32 in the console. That means our installation works perfectly and we have successfully completed step number 1. Pretty straightforward, right? Now that we have got YoloV8 installed and ready, let's move on to step number 2, creating our dataset. So what exactly is a dataset? In simple terms, it is a collection of images that our model will learn from. It is like its study material. Each image helps teach the model what we want it to recognize. For this project, we are focused on detecting just one thing, the European perch. In object detection, this specific target we are identifying is called a class. Since we are only interested in detecting the European perch, we will have just one class in our dataset, which keeps things simple. To build our dataset, I'll be using around 500 still images of the European perch taken from my underwater footage. I gathered images that show the fish in different poses, lighting conditions, and backgrounds. This variety is key to giving the model a solid understanding of the fish across different real-world situations. The number of images we use plays a big role in the model's accuracy. Essentially, the more images we have, the more examples the model can learn from, which generally leads to better performance. Each image provides another opportunity for the model to recognize unique features of the European perch, like its shape, color, and appearance in various lighting conditions. However, it is not just about quantity. Quality and diversity are equally important. For instance, if we had 500 images but they all looked similar, the model will struggle to recognize the fish in new conditions. A well-rounded dataset with enough images and variety will help the model make accurate predictions. In addition to images of the European perch, it is also helpful to include around 50 to 100 images that don't contain the fish at all. These are called background images, and they help the model learn to ignore irrelevant objects in the scene. By training with both images that contain the fish and those without it, the model becomes better at distinguishing when the fish is present and when it is not. If you are creating your own dataset, aim for at least a few hundred images of your target object, along with some background images. You can capture these images with a camera, you can use your phone, or even find suitable images from public sources. Once we have gathered our images, we organize them by placing them in a folder within our project directory. I created a folder called Images inside the Fish Detector project folder to keep everything structured. To make it easy to distinguish between images with the European perch and background images, I named them accordingly. For the images that contain the fish, I used a naming convention like image 1, image 2, and so on. For the background images, I used background 1, background 2, and so on. This naming system helps us quickly identify which images contain our target object and which don't, as we move through the annotation and training process. In my images folder, I now have a total of 508 images with the European perch and 100 background images. Images that don't contain the European perch, but may include other types of fish or background elements. This variety will be essential for teaching our model to focus on detecting the European perch specifically. With our images ready, let's move on to step number 3, annotating the dataset. So, what does annotating the dataset mean and why is it so important? Annotation is the process of labeling each instance of our target object, in our case, the European perch, within the images. This involves drawing a bounding box around every fish in each image so the model learns to recognize what we are asking it to detect. Essentially, annotations provide the answer key the model will use to learn from. Without proper annotations, the model will have no way of knowing what to focus on its image, making training impossible. Accurate and consistent annotation is crucial for good model performance. By precisely marking where the European perch appears in its image, we give the model detailed information about the fish's shape, size, and position within the scene. This helps it develop an understanding of the fish's unique features and makes it more likely to detect the fish accurately in new images or videos. To annotate our dataset, we'll use an online tool called YoloV8, which is commonly used in computer vision projects. YoloV8 makes it easy to create bounding boxes around objects and export the data in a format compatible with YoloV8. The first thing we have to do is to create a free account. So we click here, try for free. There are many pricing options available, but in our case, the free version is enough. Here is the screen we will be shown when logged in. We have to go to Projects and create a new project. Let's name our project Perch Detector. Now, we also have to add a label, a class that we want to detect. So let's call it Perch and press the Continue button. The last thing we have to do is to press the button Submit and Open. Next, we need to create a new task within our project. In YoloV8, a task is simply a set of images or video frames that we want to annotate. It helps us organize and manage our annotation work more effectively, especially for large datasets. To create a task, we click this button and then click on Create New Task. Let's name this annotation task something simple like Perch Images, so it's easy to identify. Now we are ready to upload our images and start annotating. Click here to start selecting the images you want to upload. We will be uploading all the images from the Images folder in our project, so I'll navigate to that folder and select them all by pressing Ctrl+A. Once selected, I click Submit and Open to begin the upload. The uploading process will now start. This may take some time, depending on the number of images and your internet connection speed. Once the upload is complete, we can begin annotating our images. As you can see, an image has been loaded, and our task is to mark the area where our target object is located. YoloV8 loads images alphabetically, so the images named background will appear first. As we discussed, these background images should not contain any instances of our target object, so there is no need to add annotations to them. However, it is a good idea to review these background images one more time to ensure they don't mistakenly contain any instances of the object we want to detect. If any of these background images do contain our target object, we should annotate them accordingly. Missing this could impact the model's accuracy, as it may learn incorrect patterns if target objects are present but unmarked. I reviewed all 100 background images and confirmed that no perch fish were present, so I didn't need to annotate anything there. Now let's move on to annotating our first image that actually contains a perch. As you can see, a perch fish is visible in this image. I'll start by selecting the rectangle tool. Since I only have one label, perch, it is already selected. In projects with multiple labels, remember to choose the correct label each time you create a new rectangle. Next, I will click on the Shape button to create a new rectangle shape. Now, I can click on the image to draw a rectangle that tightly encloses the perch fish or any other object you are annotating. Keeping the box as close to the fish's outline as possible ensures accurate labeling, which is essential for effective training. That's it, our first image is labeled. We can press Save to save our progress. Now we can repeat this process for the entire dataset, which in my case includes 500 images. To make the process faster, it's helpful to learn a few keyboard shortcuts. To move to the next image, you can click this icon or simply press F on the keyboard. To go back to the previous image, click this icon or press D. When creating a new rectangle, you can either click here, as we did before, or press N to quickly add a new bounding box. Pretty handy, right? Let's continue labeling. If an image contains multiple objects, make sure to label each one individually. For example, in this image, we can see two birds' feet, so I will label them both with separate bounding boxes. If the object we are labeling isn't fully visible, we will draw the box only around the visible part, avoiding any guesses about hidden portions. To sum up, follow these labeling guidelines to ensure accuracy. Every object in an image should have its own bounding box. For partially visible objects, draw the box around the visible portion only, without assuming hidden parts. Keep the boxes tight around each object, avoiding background elements or nearby objects to help the model focus. Review each image carefully to ensure no object is missed. Sticking to these practices will create a high-quality dataset and help achieve accurate model training results. Following these guidelines, I carefully labeled each image, and it took me about 2 hours to complete the entire task. With this, we have successfully completed step number 3. Our dataset is accurately annotated and ready for training. Now, let's move on to step number 4, splitting the dataset into training and validation sets. This step will help us prepare the data structure YoloV8 needs for optimal training and evaluation. Before we proceed with the split, we will first export the annotated dataset in a format compatible with YoloV8. Machine learning models like YoloV8 require data to be organized in specific ways to read and learn from it efficiently. To export our dataset, we start by clicking on the Task menu item here. Next, we go to the Actions menu, click on it, and then select Export Task Dataset. In the new window that opens, we will choose the format for our export. Scroll down the list of options and select YoloV1.1 as the export format. This format is specifically structured for compatibility with YoloV8, ensuring our annotations align perfectly with the model's requirements. Once we have selected the format, we click OK to start the export process. Depending on the size of our dataset, this may take a few moments. When the export is complete, a download link will appear. We click it to download a zip file containing our exported dataset. Next, we unzip the file into our project folder. Inside the unzipped folder, we will see 3 additional files and a folder named OBJ train data. These 3 files generated by CVAT aren't necessary for our training, so we can safely delete them. Now let's open the OBJ train data folder. Inside, you will find hundreds of .txt files. Each txt file corresponds to an image and contains the annotations for that specific image. The txt files are named identically to their respective images, making it easy to match them. In other words, for every image we uploaded, there is a corresponding txt file with the same file name but with a txt extension. Let's open one of these files, for example, image1.txt. Inside, you will see lines of numbers that represent the annotated objects. Each line begins with a class label, followed by the bounding box coordinates, which are normalized between 0 and 1. In this example, 0 is the class label, indicating the bird's feet. These numbers are the x and y coordinates of the bounding box center. This number is the width of the bounding box, and this number is the height of the bounding box. If you open the txt files for the background images, like background1.txt, they should be empty, as these background images don't contain any objects. With our dataset annotated and organized, The next step is to set up the train and val folders to prepare for training in YoloV8. First, we rename the obj_train data folder to labels. This will serve as the main folder for all annotation files. Next, we open the images folder and create two subfolders inside it, naming one train and the other val. Now we will divide our images into these folders to create our training and validation sets. About 80% of the images will be used for training the model, so we will place those in the train folder. The remaining 20% of images go to the val folder to serve as the validation set. This split is essential because it allows us to test the model's performance on new data that it hasn't seen before. By training on one set of images and validating on a separate set, we can better understand how well the model will generalize to new unseen data, an important step in building a reliable detector. I start by selecting 80 background images, specifically background 1 to background 80, and place them inside the train folder. Next, I choose 410 images containing our target object from image 1 to image 410, and also move these into the train folder. The remaining images, including both background and target images, are placed into the val folder for validation. I choose to split the data this way for simplicity. However, for better results, the validation images should be picked more carefully. Instead of just dividing the dataset randomly, it is essential to include a variety of conditions, angles, and lighting that the model is likely to encounter in real-world scenarios. A thoughtfully chosen validation set provides a clearer picture of how well the model will perform on new unseen data. Now, let's organize the txt files in the labels folder to match the images we placed in the train and val folders. First, we create two folders, one named train and the other val. We will start with the training set by moving specific files into the train folder. All the background annotations from background1.txt to background80.txt, plus all target object annotations from image1.txt to image410.txt. Then, for our validation set, we will take all the remaining txt files and place them in the val folder. This organization is crucial because YoloV8 needs to pair each image with its matching annotation file. When we arrange the files this way, the model can properly learn from the training data and accurately evaluate its performance using the validation data, helping us build a reliable object detector. With our dataset now organized into training and validation folders, both for images and labels, we are ready to proceed with step number 5, training our model. Let's open the train.py file we created earlier. Right now, it contains only 2 lines of code to confirm our YoloV8 installation. But here is the exciting part. With just 3 additional lines, we can set up and start training our model. So let's write the first one of the 3 lines. At the top of our code file, we add from Ultralytics import YOLO. This line imports the YOLO class from the Ultralytics library, which is the main class for working with YoloV8 models. Now, let's add another line here. Model is equal to YOLO in capitals, parentheses, quotes, YoloV8n dot YAML. With this line of code, we create a YOLO object and assign it to the model variable. If you don't know what an object is, or if you are not comfortable with object-oriented programming, I want to share something exciting. I have put together a course called Object-Oriented Programming Made Easy that makes these concepts click in a whole new way. Imagine building your own digital ecosystem, cells that move, interact, and even live their lives, all in just a few hours. It is a project where you will see how object-oriented programming simplifies even the most complex tasks. No more vague examples with cats and dogs. We are working on something real and interactive that will teach you object-oriented principles you can actually use. This course covers all the essentials: classes, inheritance, polymorphism, encapsulation, and even UML for organizing your project structure. And the best part, you'll finish the course with a strong understanding of why we use object-oriented programming, not just how. Check out the link in the description. If you take this course, I promise you are going to understand object-oriented programming once and for all. Now back to our code. Here we are creating a brand new model and setting up its structure. This file tells YoloV8 how to build and train the model. This file is for the nano version of YoloV8, which is super fast and lightweight. YoloV8 has several versions, each balancing speed and accuracy differently. The Nano, it is the fastest and smallest, great for quick tasks on limited hardware. The small model is a mix of speed and accuracy. The medium model provides higher accuracy for mid-range systems, and the large and extra-large models provide the best accuracy but needs more powerful hardware. I chose to create the smallest and fastest model by specifying a nano model. If I change the character from N to S, I will be creating a small model instead, and similarly I could use M, L or X to create medium, large or extra large models. Each of these model sizes offers a different balance of speed and accuracy, allowing you to choose the one that best fits your hardware and project requirements. Now we only have to write one more line of code to actually train the newly created model. Let's type this line of code. Model.train parentheses data is equal to quotes conf.yaml, epochs is equal 300. This line of code initiates the training process, but you might be wondering, how does the model know where to find the data it needs to train? We haven't specified that information directly in the code. This is where this file comes into play, this argument here. In this file, we will provide essential details guiding the model on where to find the training and validation data, as well as the number of classes it should detect and their names. Currently, this file doesn't exist, so we need to create it ourselves. In our project folder, we create a new file and name it conf.yaml. Next, we will specify a few critical configurations within this file. The first entry is the path, which points to the root directory of our dataset. We will use the directory of our project. Then we define paths for the train and validation sets, specifying the subfolders that contain our training and validation images respectively. Train: images/train. Val: images/val. Following this, we need to define the classes that our model will be trained to detect. Since we are focusing only on the perch fish, we will use names: 0, perch. We save the file and we are ready to move on. This simple configuration file ensures that YoloV8 has all the information it needs about the data, including where to locate the images and the classes it expected to recognize. Now back to our code. The last argument in this line of code is epochs, which defines the number of training cycles or epochs the model will go through as it learns. Each epoch represents one complete pass over the entire training dataset. Here we have set it to 300, meaning the model will process the dataset 300 times to refine its understanding. More epochs generally lead to better accuracy, as the model has more opportunities to fine-tune its ability to recognize the target object. However, increasing epochs also means longer training time, so finding a balance that suits your hardware and accuracy needs is key. By default, this training code will run on your CPU, which might take a while depending on the size of the dataset and the complexity of the model. However, if you have an NVIDIA graphics card with CUDA support, you can significantly speed up this process by running the training on the GPU. This can make a huge difference in training time. For this video, I won't be covering how to set up YoloV8 with CUDA, but if you are interested in learning more about it, leave a comment below. I will be happy to make a follow-up video showing exactly how to configure CUDA and run YoloV8 on the GPU to take advantage of faster training speeds. Now we are ready to start the training. When we run the code, you'll see a lot of details appearing in the console, like the current epoch, how well the model is learning, and the processing speed. These details helps us track how our model improves with each round. As training continues, YoloV8 refines its understanding of our target object, the European perch, becoming more accurate with each pass through the data. Watching these numbers change gives us insight into the model's learning process. Explaining what each of these numbers means can be a topic on its own, covering things like loss values, accuracy scores, and more. If you are interested, let me know in the comments and I'd be happy to make another video diving into these details. Since we are currently running the training on the CPU, it is going to take several hours. To speed things up and demonstrate the process, let's stop the current training and rerun it with fewer epochs, let's say 10 instead of 300, so we can see the full workflow without waiting too long. After changing 300 to 10 in our code, we can rerun the training and it should finish in just a few minutes. Once the training is complete, YoloV8 saves what it has learned about detecting the perch in files called model weights. These weights capture everything YoloV8 has learned during training and can be used to immediately test the model or even continue training if needed. To find this model, we navigate to the runs folder YoloV8 created, then to the detect subfolder, followed by train, and finally to the weights folder. Inside, we will see two important files, last.pt and best.pt. The last.pt file contains the model's weight at the very end of the last training session. The best.pt file stores the weights from the best performing epoch based on our evaluation metrics. The best.pt file is generally the one we will use, as it represents the model at its peak performance during training. Now we are ready to test or further refine the model with these saved weights. In this case, however, instead of using the best.pt file from our current training session, I'll be using a best.pt file generated from a full 300 epoch training run I previously completed using my GPU. This will allow us to see the model's performance after a more intensive training session, giving us the best results possible for our testing phase. To make testing our model easier, let's first copy the best.pt file from the weights folder into the main project directory. This will allow us to quickly reference the model file when writing our testing script. With our model saved in the project's top-level directory, we are ready to write a simple script that will load a new image, one the model hasn't seen during training, and test if it can correctly detect our target object. For this test, we will use two images to evaluate the model's ability to detect our target object, the perch fish, in various scenarios. The first image, named test.jpg, has a clear view of a single perch. This setup will allow us to see if the model can easily detect the fish when it is clearly visible and isolated. The second image, test2.jpg, includes multiple perch fish positioned at different angles and scattered across the scene. Some may be partially obstructed or overlapping. This image will test the model's ability to detect multiple instances in a more challenging, realistic setting, giving us insight into how well the model generalizes to complex scenarios. Now let me show you how easy it is to use this model. Let's start by creating a new Python file called test.py. You won't believe it. We only need 4 lines of code to test our model. First, we import the YOLO class, which lets us load and run our trained model. From Ultralytics, import YOLO. Next, we load our custom trained model, which we saved as best.pt. This model has learned to recognize the European perch fish. Model is equal to YOLO in capitals, parentheses, quotes, best.pt. Now we pass an image to the model for it to make predictions. In this case, we will use test.jpg. Results is equal to model, parentheses, test.jpg. Finally, we display the results. Results bracket 0.show. And that's it. Just 4 lines and we are ready to see our model in action. Now let's run the code. Look at that, it's working. The model successfully identified the perch fish with a confidence of 76%. The bounding box looks accurate too, right around the fish. Simple, powerful and effective. Now let's test the model with a more challenging example. We will switch the image to test number 2 JPEG, which contains multiple perch fish in different positions with some partially hidden. To do this, we just change the file name to test_2 JPEG in our script and we run the code again. As you can see, the model did quite well. It successfully identified 5 out of the 6 perch fish in the image, missing only this one right here. This result shows that our model is learning well, but could still improve in complex scenes. To make it even more effective, we might consider training it with a larger model architecture or adding more variety to the dataset for enhanced accuracy. Now, for the last demonstration, I'll show you how this model performs on video footage I captured. YoloV8's real-time detection capability is perfect for videos, making it an ideal tool for scenarios like tracking fish underwater. In this example, you'll see how our model identifies multiple perch fish across different frames, adjusting as they move and interact with the scene. Let's run the video test and see the model in action. As you can see, the model does a great job detecting the fish when it's close to the camera, but it starts to struggle when the fish is further away, where water clarity and distance can make the fish harder to identify. This shows us that the model is performing well in ideal conditions, but may need further training or adjustments to improve detection in more challenging scenarios, like detecting smaller or partially obscured fish at a distance. Keep in mind, we are using the smallest YOLO model, the nano version, focused on speed and efficiency. It does well up close, but if we want to improve detection for fish further from the camera, we could try a larger model like YoloV8 Small or Medium, which will capture finer details but require more processing power. And there you have it. We have taken a custom object detection project from start to finish, collecting data, annotating it, training a YoloV8 model, and testing it to see the results in action. This process shows just how accessible custom object detection can be with the right tools and structured approach. If you found this tutorial helpful, please give it a thumbs up and consider subscribing for more content on machine learning, coding, and custom projects. Let me know in the comments if there is anything specific you would like me to cover in the future, whether it's training with different YOLO models, optimizing performance, or diving into other areas of AI. Thank you very much for watching, and I'll see you in the next video.